good afternoon, everyone. You're in for a very deep dive into a very technical talk. I see you all have the courage to stand with me in this challenge. It's not a very big group, but we'll deal with it. So I'm Albert Groothedde. I work at Kadena. Kadena, the scalable blockchain. I'm the architect of the developer experience squad. Kadena is a scalable blockchain that has solved the trilemma of security, availability, and distribution. So that's really nice. I'm going to talk about the Kadena Client with you. So the Kadena Client is a client that can interface with the blockchain in a type-safe manner. And what it does is it allows you to build transactions, sign transactions, and submit those transactions. So it's actually three parts that work together. And the generation is, of course, done via a CLI and a library that we use for that as well. So who knows what these images are from? Anyone? I know there's one person that definitely knows. Yes, the expanse. So I'm going to take you down the road and through the ring of teleportation into the world of parsers, lexers, and syntax trees. And yeah, so this is the expanse. So let's imagine you like watching movies, and you have a subscription. And instead of having to file your credit card, you file your account that is on the blockchain, and you make an agreement on the blockchain with, for example, Netflix, to pay your bills for what they have to offer. So let's go into that and see how a smart contract would work, and how we can then create TypeScript definitions in order to work with the blockchain on your front end. So for example, here we have a subscribe function that is part of the smart contract. And here you fill in your account and the amount of months that you want to subscribe for this service. We could make it more, elaborate, where we say, okay, only for the specific movie or specific amount of time that we want to work with that, or that we want to watch. We, do a continuous subscription that actually only charges you for the moments that you are actually watching. But for the sake of simplicity, we do it like this. So this one has two arguments, account and months. And in our case, the month part is part of a schema. We have a function that's available on this smart contract. And when we file, our subscription, we basically store this via a key value pair. So in this case, the key is the month, the account of the user, and the value is the amount of months that we want to subscribe for this thing. And this is then stored in a database. And this database belongs to the smart contract of StreamTV. Let's call it StreamTV, right? Now, in order to do this, we also use another smart contract that's also on the blockchain. So it's kind of like a library that you use from something else. And inside this, subscribe function, we are calling the coin.transfer function. And here we are calling it with three arguments. One, the sender, which in this case is my account, the receiver, which in this case is StreamTV, and the amount of months times $4.99, or whatever currency you want to use. Under the hood, when this call happens, it will make sure to import another module that also exists on the blockchain, in this case the coin module. And it will execute the function that is written here. And then store this information of what you actually did, so deduct the balance and increase the balance of the receiver, and store it in the schema, in the database. So what is a smart contract? Quick overview. So it's a piece of code that's stored on a decentralized platform, a definition of a schema, and functions to interact with that schema. And each function can restrict the operations on the records in the schema. And it can do that in a very scoped way, which is what we're going to talk about. So in short, a set of serverless functions, we all know serverless functions, that can interact with a database on a decentralized platform. So this is all nothing Web3. It's just Lambda, But then, a little bit more. So who has worked with blockchain before? I know a few people. Right. So let's stick with this definition and start with Pact. So we are using Pact on the smart contract language as smart contract language on the blockchain, on the Kadena blockchain. It's a Turing incomplete language, which provides us with some benefits. Turing incomplete means that it limits the amount of things that you can do. In this case, for example, there is no recursion, there's no loops. If you have no recursion, it means that you can not get into an infinite loop, where you only apply a modification or something on a set of elements in an array, because that is possible. The second one is that there is no recursion, so there's also no problem of, for example, Stack Overflow errors, which is really nice. And because of this, we can make smart contracts 100% testable with all the options available. And also in Pact, you can give each function some models. And these models are limiting the things that can happen inside that function. And because of these models, we can also generate all the possibilities. So we can create a finite set of possibilities and then verify that we actually end up with the result that we expect. And that's done like this. So here, let me see. Yeah, so here, in this case, we see that the transfer function is a function where it conserves mass. And this is actually another function, but what it means is that it will take all the balances of the coin, let's say, table, and they end up with 0, which means that there is no added money out of thin air, and there is no reduced money out of thin air. I mean, yeah, destroyed money, so to speak. So the transfer function can only stay into effect when this has happened. So if we make our body of the function where this is not true anymore, and we run the form of verification, it will break. So this is a very secure way to do that. Now, there is also a nice website called savedbykadena.org, where we can see all the products and projects that might have lost a lot of money because they aren't using Pact, basically. Or they aren't using proof of work, because we are using Pact with proof of work. So, quick recap, smart contracts, and we are going to look into a definition of a schema now. So what does a schema look like? So here we have a schema, and inside the schema we have two values. So I already said there's a key and value pair. So the key is not written here, but the value is actually the balance and the guard. And this is specific for the coin schema. So in the coin schema, we only specify the balance and who can actually change that balance, because that's protected by the guard. Now, there is a hidden property, which we don't define because it's always there for every schema, and that's the key. So in this case, the ID. And here we can see that the ID is, for example, a name. In this case, my account name. An account name can be anything with some limitations. The value is actually the balance and the guard. So the balance is just the amount of token or coin or KDA or Kadena coin is that there is. And then there is also a guard of who can actually change this record. Now the guard is usually something that has a key. So in this case, this is a key guard where the predicate says that all the keys need to sign when there is a modification being executed on this balance. So this is the key, and this is actually the public key. So you need to sign with your private key, and then it can be verified with the public key. Now that we spoke about the definition of a schema, let's look into the functions to interact with the schema. So this is a function on the blockchain which is actually the literal, well, there are some parts omitted, but this is fairly straightforward. And this is also what is actually on the blockchain. So there's no conversion to bytecode, but you can actually read this straight from the blockchain, which means it's also very accessible. Now, the signature of this function, and that's important because that's what we're going to use, is a transfer function with 3 parameters. In here, we have several guards. So here we say, okay, the sender and the receiver need to be different. The account for the sender needs to exist, and the account for the receiver needs to exist. Also, the amount of money that we transfer from the sender to the receiver needs to be positive. Otherwise, we are basically retrieving money when we do a transfer. That's something that you don't want, of course. Now that we looked into the functions, we're going to look into how a function can restrict the operations. So here we have the function again, and we can do that with the with capability statement. And with capability actually introduces something that in the transaction, when we submit this transaction to the blockchain, there must be a signature that is specific to what is written here. And then when this is actually there, this function will be executed, and when it doesn't fail, it will continue to the code block. So here we have the capability, which is sort of a guard, and then we have the code block. So the code block will be executed, and it will actually debit the amount from the sender's account, and it will credit the amount to the receiver's account. So how that works is, if we do a coin.transfer, so pact is actually a Lisp dialect of a language. When we do a coin.transfer from Albert to John with this amount, we actually check if those guards are there, but also if the capability is signed for. And once that's done, we can actually execute what is happening here. So we debit this one, and then we credit this one. So let's take a more detailed look into what a capability is. A capability is something, so this is actually a transfer. So this is a transaction that we submit to the blockchain. Of course, there are some other properties, but this is the relevant part for a capability. Because it's essential to understand why we need this in order to understand what we need to create for the type definitions that we are going to make for the client. So here we have a coin.transfer, and we're actually defining that whoever is doing this transfer needs to sign for the public key that belongs to Albert, in this case. And that matches with the functions with capability that we see over here. So this one needs to be signed for. And what we see when we continue with that is that we have a signature. So here we have a list of capabilities that need to be signed for. And those are part of the signers and the signatures, and those match. So the amount of signatures that is in here will usually match the list that is in here. So if you sign for something, you will sign for whatever matches to the signature that is matching in the index of the SIGs and the signers. So in this case, it is signed for, basically. So why do we need a JavaScript client, right? Well, we also know that we have Prisma. So let's say we have a backend with SQL and a database with tables, and we can usually, just write the SQL for ourselves. That is all good, but it's kind of cumbersome. So, and the same thing is for transactions on the blockchain. So we have a front end, and we build up our transactions, we send it to an API, and it will be interpreted, and it will have its effect on the blockchain. Now, actually, we do a lot more, because we don't just send transactions, but we also need to sign them. And signing is a whole process on itself. So we want to create that functionality and add that to the client as well. So what we actually want to do, we build a transaction, we sign it, we send it to the blockchain, and then also we want to, because blockchain is, there's a process going on to validate your transaction and to mine a new block. So this needs to be, you wait for it to be validated. And all this together brings us to this. So basically, but also, when we are building the transaction, we're actually writing the code. That's only a tiny part, which is relevant. But we also need to add the relevant authorizations. So when using the client, we can offer IntelliSense for that. And we also need to set some parameters like which network are we using, which chain are we using, who is going to send this transaction to the blockchain, who is actually paying for the transaction costs, etc. So for the backend, we actually use Prisma, and Prisma Generator and Prisma Client. And we can do the same thing for the blockchain as well. So in the blockchain, we generate from the smart contract the client type information, and with the front end, we can then interface with the client to use and send and communicate with the blockchain. So how does it work? So in the front end, we actually have a transaction that's being built with a builder. And then we say, okay, we want to execute something, and in this case, we want to do a transfer. So this is the goal, right? We want some IntelliSense to give us some information on what are the possibilities within the smart contract. So in this case, if I pre-type this with transfer, you see that there is a transfer create possibility, a transfer, and some other things. You can see of this as a REST endpoint, where you, if you generate from Swagger or something, you also get this information, and you can build up your API call, let's say. And here we also see that there is 3 properties. Now, these 3 properties, or this function, actually returns something, which is actually the return value that we saw from the blockchain, but it also returns an object that starts here, which is actually a capability for transfer and for gas. So the gas capability is who is going to pay for the transaction cost, and the transfer capability, transfer capability is who is going to authorize for transferring money from one user to another. And that is what we're actually doing here. So this is similar to, for example, a jaw token or a bearer token or something like that, which is sent with the transaction to the blockchain. In this case, we have coin.gas and coin.transfer. And these need to match in order to make sure that we can actually do this transfer. And then also, like I spoke about, we have some other information that has value. So how do we do that? So basically, we have a smart contract, and we're going to parse it, and then we're going to generate some TypeScript definitions from that. And now I'm going to take you a little bit into the teleportation of the black hole of parsers. And I need to switch my screen for that. So let me see if that works fluently. This is not what I wanted. So this needs to be main. Yes. And I need to mirror like so. So a little bit of, I'm going to take you into a little bit of how a grammar works. It's not exactly what we use, but it's similar to what we do. So let's see. We have here something that defines a number. And a number is then defined by 0 to 9 and then infinite times. So here we can see that it matches 1, 2, 3, 4, but if I add a p or another character, it doesn't match anymore. So that's how a parser works. It will check whether it matches. If it doesn't match, it will go back and see if something else might match. So if I say I want to have numbers or a p, then this would match, right? So it now goes from the first to the second in order to make sure that it matches. Now, this is, of course, when we just have numbers, this is, of course, not a very useful way to parse a number, because we actually want this as one thing. So what we can do is we can add some processing on top of that. So here we say, okay, the data that we get in, it's actually the amount of things that we have here. So here we have the first section, and that is the first element in that array. And we're going to join them together with nothing, and which means that we will now have just this part here. So how we do it for an operator is similar. And here we say, okay, we have the plus and the minus, and they work on its own, but now we have no way to add numbers, because we want to add 1 to 1 in this case, but this doesn't fit what we have there. So how we do that is that we combine these two together. So let me just copy this part. And we add it here. So now we have two definitions. So we have an operator definition and a number definition. And we're going to use it. I actually need to use this one, otherwise we get... And then we say, okay, now number, operator, number will actually match. So this is actually how we are going to go about parsing our smart contract as well. You can add a lot of other information here. So for example, here we said that the operator that we have here is of type operator with the value sum. Well, you can add some other modifications to it. And then you can interpret this and use it to do, for example, do some assembly on this. That's actually how parsers usually would work. So let me switch back to the presentation after this short detour. Stop mirroring. And now we have it back. All right, awesome. So in this case, we have a smart contract on the top, and this is the output that we want, right? So we have def and transfer, some parameters, and then those are defined here. Now, as you can see that defen is the identification for, it's a keyword for identifying what comes next, and what comes next in this case is a function. So we have a function name and a value that is the return value. So that's actually what we see and highlighted here. And we also have some parameters. So this is the way how we parse them, and this is the way how we can use them to build our TypeScript client. Now on the right, we see, so here we have still this function, and on the right we have now actually the grammar, so to speak, of this function. So a method is defined by a block. So first we have the block part. A block means that it has a starting and an ending parentheses. That's it. Very simple. And as long as all the following things match, we know we're still on the right path to finding a method. If it doesn't match, well, then we need to look into another parser. So here we see that, actually this is not jQuery, by the way, but it does something because we are taking this value and we use this value that we added here because it's essentially we can just use this part, but that means that we are not extracting this information into a JSON object. So what we do here is we actually have some of those properties and that match with the keys that we use here. Now, let's start with the first one. So whenever the kind is a defen, then we can use, we can define whatever it is. If that matches, then we go to the next one. In this case, the name. So we are expecting to see an atom. An atom is just a, usually an atom is described as a structure of characters, just a string, but not denoted by quotes. So in this case, this is an atom. Now, maybe, because it's not mandatory, we have a type definition here. So that's why it's wrapped in a maybe, and we want to store that as a return type. So we store it here as a return type. And we do the same for a sequence, and a sequence is automatically being wrapped into an array. So because the parameters contains a sequence, it will automatically be part of an array, and that way we have basically parsed this small part of the signature of the function. And we do the same for the capability, but I won't go into depth for that one as well. So this is actually what we have as the output. So we have a coin, which is a module, a type of module. So does anyone has some experience with ASTs, abstract syntax trees? No. So this is actually similar to how an abstract syntax tree would look like. So if you are parsing some JavaScript or TypeScript code and you want to do some modifications to it and put it back, then you would probably use a syntax tree. Now from this syntax tree, we actually want to make a type definition. So this is a type definition for the smart contract for the client. So what does it mean? So here we have, so basically we just generate this with a text concatenation, string concatenation. Very simple, very straightforward. But we can do that because we have all the information neatly prepared here in the parser output. Now if we have some parser output, you can see the name of the module is coin. So we store that in the interface called IPAC modules. The IPAC modules is then in turn used inside the client. And that's why pack.modules is actually this interface, and it has a coin property. And inside there, we also have a function called transfer. And we have some parameters. So we can all do that. But also, I actually skipped something here, but we also have a set of things that refer to the capabilities. And the capabilities are the things that we want to get IntelliSense from. So when you are going to sign for something, you want to have the information readily available. And the thing is that here we use types, but you can still use this function, this runtime code, without the type information. And that's really powerful because you can, if you know enough about the blockchain, you can still use the Kadena client without having to generate all the types. And that's the reason why we chose to just generate types and not generate a full client. Oh, here you can see also that coin.transfer is not only adding this as a possibility to sign for, but it's also adding all the arguments that you can add. And you get IntelliSense for that, which is really nice. So this would be the final version of that transaction. So here we can still see how it's matched to whatever is on the bottom. So that's basically transaction building with JavaScript. So what did we do? In recap, we have built an expression builder where we can make expressions based on the signature of functions in the smart contract. We can then also build the transaction up with more components that we need in order to make a complete transaction that can actually be sent to the blockchain. We also added signing utilities. That's something we didn't spoke about yet too much, but it's utility function where you can send the transaction that we have created here with the create transaction function and send it to Chainweaver or Echo Wallet or the Ledger, or now I need to call all the wallets because otherwise people are sad. And then we also have a client for the blockchain, and this is really neat because when you are sending stuff to the blockchain, you want to know whether it's verified, whether it's actually there. And this is what we use for that. And you can also submit a transaction using this and then listen for the response, which is actually the request key, and see when it's being mined. And then you're finished. So that's really cool. So how do you sign transactions? Well, we have a few wallet providers. And this is really nice because we're actually giving away an NFT, specifically for this talk, that can everyone can claim, but also for a unique NFT. Unique NFT made by Steven Streetemans. And this is actually, so that's what we did. The front end It's closer to the blockchain than you thought. So yeah, you can all use it. And if you scan this one, you can actually claim this one, and it will show up in your wallet. And you will be able to, show, hey guys, I have been here. I have been to this conference where you were able to claim this NFT. So it's kind of a proof of attendance. And there is also a raffle, so a lottery basically, where we are giving away this wonderful capybara, the legend of Jan Haring. So thank you very much. If you have any questions, fire away.